looking at ways they were thinking about it and maybe guiding those students to figure their ideas, the concept. So he just completely went for people who have the correct answers.
Okay. What other? Yeah, Richard.
And also, like with mathematics, the whole foundation is connecting ideas.
Okay.
And what he did was he just kind of had a discussion of show and tell of here's how I did this problem, but he didn't lead it into anything. He didn't connect ideas. He just called on, like he didn't sequence them. He just kind of randomly showed different methods.
Okay.
He didn't make any connections to the students.
Okay. Let's see. So Bennett.
One of the things also only showed one method. It didn't show varying branching approaches. It only showed a correctness. Like this is the correct way.
Okay.
There was no like discussion or question of other ways.
Okay.
He didn't explain how to get the answer, or there was no different discussion of other methods, or he didn't check for other students' understanding.
Cool.
I liked the article because as a teacher or as a person who's trying to become a teacher, I haven't had a lot of experience with doing that method of teaching numerous times. And so what the article is getting at is setting up kind of like a framework for teachers who want to teach this way, but are unsure of like how to assess themselves. So I liked it because I felt like, oh, now I have something that I can reference and kind of look back to and check myself on when I try to teach this way.
Okay. Carter.
And to tag along with that, I really like how it talked about how you're not going to go into a lesson that you've always seen taught computationally and be able to necessarily 100% lead the students successfully like this, that it takes practice to learn how to instruct this way.
Okay.
To the point where they said to anticipate student responses.
Okay.
And if you haven't asked students these type of questions before in this manner, it's going to be hard to anticipate it.
Okay.
And I've had that worry at first too, where it's like, if I try to start doing this, am I going to get things I'm not expecting and not know where to go with it? And I really liked how this article talked about that and said, you won't be perfect your first time. If you get those questions you don't know how to answer, be honest with the students. Let them know that at this time you want to give a little bit more thought to it and return to it on another day and sideline that and continue on the path that you were anticipating to still build their thought. And then, you know, future time when you do that lesson again, okay, this is a possibility I could get. How can I elaborate on that?
Cool. Nice. Grant?
I like the fifth stage about connecting the ideas between different approaches. So after like having different approaches, linking them together and showing the common mathematical structure of why you can do it different ways. The common theme is.
Nice. Matt?
I like that it just always challenges students. I mean, like if you set it up right, I mean, you're constantly getting harder and harder where it can go really anywhere, and it's always challenging them up. Well, where can we draw another connection from here? Not just did you get the right answer, it goes a lot past that, which I like.
Julie?
Yeah, piggyback off what you said about the different ways of representing the math. That's totally like the different learners different types of learners that you have, the different intelligences. You've got visual learners who would benefit from a visual or a picture. You've got logical learners who would benefit from a T chart or a table or something like that.
Good. Daniel?
I liked how you really have to know your students' thinking in order to comprehend why they chose that path. Because if you can help them, if you can help understand why their path is incorrect, it can help lead to more self-discovery and like, oh, okay, that's why it doesn't work.
Okay. Those are all great comments. So there was a visual in the article. So what were do you remember the 5 practices without looking?
Anticipate.
Okay, hold on a sec. So hopefully we can get this.
Exactly.
Oh, it's
up.
sweet. Okay, what was the first one? we go. Okay, anticipating. So there was an image like this. Okay, and then what was next? Monitoring. So what? So someone you knew. How would from this table have been clever? So Jessica or Kyle or Anna. What was anticipating?
Like anticipating, like thinking ahead of what students might come up with, like questions or troubles they might run into.
Okay.
Having thought that before actually.
Okay. All right. And Kyle, what was monitoring?
Monitoring was watching over the students and trying to make sure they're understanding the concepts.
Okay. Is that what we saw monitoring is? Making sure they understand. Victoria.
Just like walking around the classroom and like just trying to figure out like the discussions going on, or like if they're discussing it, or like what they're writing down on the papers.
Okay. Maria.
What I also mentioned about monitoring, it's not just walking around making sure that they're doing what they're supposed to, or talking about the strategies. It's also going to each table or group and questioning them and asking them what their thinking is.
Okay. So monitoring is about gathering as much information about where each group of students or each student is at, right?
Right.
Okay. What was next? And how about Danielle? What was selecting about? Remember?
Picking students who had different approaches maybe.
Okay. So want to say more about that, Daniel?
You can use it. You can choose students who got the wrong answer, so you can lead out the misconceptions about the problems.
Okay.
Like with the caterpillar one, like some people did, what was it 5 times 12? You can bring that up to the entire class. Like, well, is that correct? Is it for every 2 caterpillars? Gonna, bring out the misconceptions about the problem.
So it's not just finding the best thinking and the best solutions, but it's truly selecting.
And then selecting and then somebody that's running responses that you've heard that show the mathematical ideas that you're trying to teach.
Okay, and also finding good thinking too. Okay. What was next? What was it?
Sequence.
Okay. Raymond, you know what that was?
Based on what I read, sequence is when the instructor decides which student will present their solution first.
Okay.
Like setting an order of who's going to present the
Okay.
solution first. And by this, he said by this, you can concept like if someone has a more complex solution, you can leave it at last, so you can work the easiest solution to the hardest.
Okay. Rochelle, what were you going to say?
I was just gonna say it's a way of guiding the rest of the lesson by being choosy or being clever about how you have students present. So like Raymond was saying, it can be from the most common solution up to like the abstract solution, or it can be from even a common misconception gathered back into what the idea was. So sequencing and selecting are really, really closely connected because you have to first select and see what you've got, and then the sequence is just kind of putting it together so that your lesson is coherent.
Okay. Bennett, were you going to chime in or same thing? Okay. Carter?
It's kind of along the same lines, but it just kind of goes along with the idea that it's important for the students to develop the idea.
Right.
So based on what you observe, what you monitored, and the students you're going to select, you place them in an order that helps them discover the concept as opposed to being shown it. So that way you see this student had this form of thinking, and now this one went a step beyond it, and this one went a step beyond it. So they take these steps and see how the big idea comes into play.
Okay. So that would be one way to sequence it. So it was the sequencing kind of open-ended depending on the goal, what the teacher's goal is. So you've got some maybe common errors that you've picked out when you've selected, and then you've got ones that are kind of showing the concepts and the connections that you're intending, and so it's just kind of like what will the best sequence be to that will help students and make the most sense and not be confusing, and then develop the idea, and then what was number 5? Okay, who wants to talk about that? Connecting?
That's kind of what sequencing was. It was building these ideas on top of each other by connecting all these methods together. And then you connected these methods to the main idea of the lesson.
Okay. So my question then, so good job. So that's good. Why was this illustration, this diagram of the 5? Why was it created in this way? Why like this? Grant.
They build on each other. So anticipating is at the core of it all. So to better monitor your students, you should be anticipating their solutions.
Okay.
And then selecting builds on monitoring, which builds on anticipating. So it's kind of like a stage diagram.
Okay. Any other thoughts on that? I would say even stronger than that. So yes, that's the right idea, but I would go a step further. Anybody want to chime in? Kyle.
I was gonna say each practice gets more and more important. It's more significant.
Okay.
The actual outcome of the whole thing is being able to connect the idea.
Okay. All right. Cool.
Kind of like the steps, instead of going like one step at a time up, if you look at it from like outwards in, so to have like a whole effective discussion, like classroom discussion, to like hear students like understanding that concepts, you have to have start. So you have to, if you have connecting, then you have to have all 4 below that too.
So in order to have connecting.
In order to have like, so it's almost looking at it as a whole and thinking it. So in order to have this whole effective classroom discussion, you have to incorporate all the parts going into starting with anticipating.
Okay. Cool.
So it's kind of reverse.
Other thoughts about why it was illustrated this way?
I would say that it's centered on students thinking, and I think all of that just ties in with what your students are thinking. You as the facilitator of this lesson, you're making sure that every single one of the students is focused on these, or you're focused on these steps with each one of the students. The questioning, the thinking, the ideas, the connecting, just all that is intertwined.
Yep. It's good. So so not only is say monitoring built on anticipating, it's selecting built on monitoring, but you can't select. You have to have monitoring in order to select, and you have to have selected to be able to sequence, and then you have to have your sequence able to connect. That makes sense? So as you move out, they're all absolutely dependent on the previous. Okay. So now we've read 3 articles. We talked about read the vignettes about calculational versus conceptual teaching, and then last week's what's that? Think through a lesson. Yeah, think through a lesson. And then now this one, the 5 practices. So why have we chosen these articles for this class? What does it have to do with technology and visualization?
It has more to do with teaching.
Has more to do with teaching.
Kind of has to do what you showed us that first day, where you just showed us. I forget what it was, but you put something up. Does this make sense?
Okay.
And that's like trying to make connections without all these steps.
Okay.
If you have these
Nice.
visuals and technology without the backup behind it, it's not helping.
Okay. Cool. Excellent. Maria.
I think we also want students to look outside the box and use different strategies to think of certain concepts rather than just paper and pen and just trying to work something the way the teacher did it.
Okay.
Rather we have these visuals where we can teach them, different ways of how to learn the concept.
Yeah, excellent. Bennett.
Also, we can create some challenges and tasks.
All right, sorry, you start over nice and loud.
Making cognitively difficult tasks for the students.
So technology lends itself to making tough tasks. Yeah, sure. Michelle?
Oh, no, I lost it.
Okay.
Sorry.
Any other? Yeah, so it's so the purpose of the technology and the visualizations is to foster this conceptual learning. So we want to keep this idea of going for the development of ideas in the forefront as we're learning about the technology and learning about graph and calculator.
Okay, sorry, I remember what I said. These 3 articles and kind of like what we've been doing in class are really testing our ideas or our own thoughts of what it means to teach mathematics in a way that inspires mathematical thinking as opposed to robotics.
Right. Excellent. Yeah. So again, as we're learning about visuals and learning how to make them, this is our goal is always developing ideas, listening to student thinking, and helping them become better problem solvers and critical thinkers. Okay, any other comments about articles in general or this article? So I want to take you through a lecture that I do. I do it with my calculus class, and it's on constant rate of change and linear functions. Did I do this? Did we do this in 482?
Yeah.
Yes.
I think it's better.
Yeah, we're gonna do it again. We're gonna do it again. Okay. All right. So you have different hats on as we go through this. You've got your student hat. You're a student, and I'm the teacher, and we're going for understanding of constant rate of change and linear functions. And then you have you've read these articles, and you're thinking about how technology is being used. So you're watching how I use the technology, and then also this idea of listening to student thinking and getting you actively involved and having you work on things yourself. So all this is part of what we've been talking about in this class. So you're kind of observing as you go through it. You're also outside of it observing. Okay, does that make sense? All right. So here's a scenario. 2 painters have started painting their respective houses at a certain point. First painter has already painted 250 square feet. The second painter, P2, has already painted 400 square feet. Okay, so something's not showing up on this screen that I want to make sure shows up here. Does that show up now?
Yeah.
Got some vertical lines now? Okay, so okay, look at that. Okay, so how might this what you're looking at represent the given situation? So, Raymond. So this, I'm showing you a purple bar and a blue bar, or maybe dark pink and indigo, or something like that. How could this represent the situation that I put in the original setup here about the painters?
Probably the painter 1 would be the one with the tortoise, and painter 2 would be the monk.
Okay. So painter 1 is the top bar or the lower bar? Okay. So what I'm hearing you say is this is the amount painted by painter 1. And this is the amount painted by painter 2. Jessica, did you have your hand up?
Oh, I was just going to say it looks like the shorter one is just a little over half of the other one, which is consistent with the story.
Okay, so if this was 400 and this was 250, this would be more than half of that. So is there a way we can be more sure about this? So is there any other clues that indicate that what we've said is correct, Stephen?
It looks like each green line represents 100 square feet.
And would that be consistent then with the information given? Okay, yeah. So each of these vertical lines is 100 square feet. So painter 1 down there is up to 250. Painter 2 is up to 400. Okay. So question: is the total amount painted by painter 2 proportional to the total amount painted by painter 1? Is the total amount painted by painter 2 proportional to total amount painted by painter 1? Julia, what do you think?
Yeah, so far.
So far.
With the information we have, for every 250 square feet that painter 1 is painted, painter 2 has already painted 400.
So for every 250 that painter 1 is painted, painter 2 will paint 400. What do you think about Julia's? What's Julia's?
Right now, that could possibly happen, but we only have one point in time.
Okay.
So we can't know for sure if it's going to remain if it will turn out to be proportional.
Okay.
Because at this moment in time, we know that painter 2 has painted 400, painter 1 has painted 250. But if you gave us another one that said painter 1 has now reached 500, but painter 2 is only at 600,
okay,
then it's no longer proportional. You can't declare things are proportional with only one moment in time or one set of relations.
Danielle?
But wouldn't 0 hours and 0 painting done count as a point in time?
Okay. So she's saying that when painter, so you're saying when painter 1 had painted 0, painter 2 had also painted 0. Okay. What do you think about that, Victoria? Agree?
Yeah, I think that's an interesting point to bring up.
Okay. Kathy, what do you think about that?
They start at the same time.
What's that?
I'm thinking about that they start at the same time.
This is the information that we have.
Yes.
Janae?
Well, I'm envisioning that they started at 400 and 250, so maybe that they'll finish with 5/8 because of just how it's going to continue following, because both of them are going at the same time, and so maybe it'll catch up with 5/8.
Okay. Yeah.
I was gonna say, we don't necessarily know if they started at the same time.
Okay.
Because even though, like, at this point, after this many hours, it's they both already painted. What if, like, one started before the other, and now it's just at this certain point in time there? So it doesn't, like, specify that they started at the same time.
Okay. It's Jackie, right? Yeah. What do you think about what Jackie said?
I agree. I mean, we can assume this, assume that, but we need a solid point. I mean,
Okay.
come time to facts.
Okay, so it sounds like some of you want some more information to answer this question. So I'm going to let painter 1's going to paint 200 more square feet. Okay, so here's painter 1 going to paint 200 more square feet. Maybe. Maybe. Come on, there we go. Oh, had it. Okay, so now I want you to talk amongst yourself about this question. Is the total amount painted by painter 2, and we're going to call that total amount Y. Y is the total amount painter 2 is painted, and the total amount painted by painter 1 is X. Is Y proportional to X, or is the total amount painted by painter 2 proportional to the total amount painted by painter 1? Go.
So you paint another.
Yeah.
Painter 2 did.
Yeah. And then there he did another 100. So
We did another 2.
Bottom is 200. Top is 250.
So we have 2 moments in time now. We have 400, 250, and we have 650.
Yeah.
450.
So
Are those
they
the
don't have
same?
to report.
Are those the same ratio? Is 650 to 450 the same as 400 to 250? 400 divided by 250 would be 5 is 4. Or 8.
Oh yeah, and then
Where the both
50
is
over
proportional.
If
It's both, if that was
they're both 8/5 proportional, so it is 650.
650.
You can't say anything about what did you use here. We don't know.
Not all that's an statement, not linear.
No, they're not. Now, 113.9 the other
13.9 is the new one. It's at what 650 and 4.
Yeah, neither can kind of change.
Well, in our case, he's running their proportional.
There's 3 different ways to turn it. So it depends. Depends on which way you're thinking of it. The way I'm thinking about it doesn't match. Because we have 400 and 250, which if you turn that into a ratio, you get 8/5. If you turn 650 over 650 and 450 into a ratio, you get, what's that, 13/9.
Maybe you are a little off. I'm pretty sure.
So let's look at the rate.
250, right? Between the two, first, you went up 200. You went 250.
They aren't proportional to each other. But
So that increased by 40%, and that increased by.
Their increase could be.
I'm also looking at it as like percentage wise. How much did they increase over the period? So the painter 1 increased by what did I say? 40%. The other one is.
How'd you get 40%? That looks like more than 40% to me.
100 over 250.
You went
No,
200.
it increased 200.
No. I'm talking about painter 1.
Painter 1 at the bottom.
Yeah, painter 1 started at 250 and increased by 100.
No, it increased
200.
200. Because each of those
Look,
little,
each of
like,
those sections is 100. They're not 50.
Oh yeah, sorry. Okay.
Okay, so I'm going to kind of fast forward. So I might ask some more questions at this point and kind of to see if I can conjure some numerical analysis out of you. So let's just skip right here to a table. So amount that painter 1 has painted. What's one value that we know? 250 corresponding painter 2. And now we have another point 2, right? Which is?
450.
And what do we conclude? Is the total amount by painter 2 proportional to the total amount by painter 1? No. Okay. All right. So why might I have chose to extend these bars with a thinner bar? So if they painted more here, painter 1 painted 200 more. That's showing as a thinner bar. And similarly with the corresponding additional amount by painter 2, what might I be showing by that? Somebody else? No, I love the enthusiasm. I just want to. What do you think, Daniel?
Well, it looks like for painter number 1, on the first bar, it was a little over 200.
Okay.
And then the thinner bar is 200.
Okay.
If you look at painter 2, the first bar was like way bigger than the thinner bar.
Okay.
And it was just a little bit more for painter 1, so it should have been longer for the thinner 1.
If proportionality was maintained, right? Okay, so it helps you. So what does it show? What is it helping to see? So it's helping to see what? Yeah. Okay, right. So yeah, so it's something changed, and we can represent that by. So now let's talk about the changes. How about the change in the amount painted by painter 2 and the change in the amount painted by painter 1? It's different quantities, right? These are different quantities now. Are those proportional? Kyle says no.
Well, I'm
Why
saying
not?
that there's a change there of 250, and for painter 2, and then painter 1, there's a change of just 200.
Okay, other reactions to this? Carter, Murray,
That's exactly what she said. Right now we
need
don't
more
have
info.
She's going up 200.
Okay. So now I'm going to have painter 1's going to paint 300 more square feet. Okay? Ready? Oh, I almost totally nailed it. The first try. Did I get it right? Yes. Okay. Talk. So now we're asking about comparing the changes. So let's write some numbers on here. This was 250, and this was 400, and then we had 450 and 650. Okay? Take it from there. Go. So now the question is, you decided that the total amount painted by painter 2 is not proportional to the total amount painted by painter 1. What about the change in the amount, or delta y? Is that proportional to delta x? Go. Talk it over. See what you think.
What is that? 300. The next was change.
That's 325 for painter 2.
375.
375? Yeah, 375.
So it's a change. So it's 300, 375. Yeah. 200.
Give us what? 250 over 200 would be 5 fourths. No, 250 over 200.
Oh,
5 fourths. And it is 300 to 375. 5 fourths. Or 375 to 300. 5 fourths. Yeah.
Okay, so it's like one thing.
We're in change.
So you need at least 2 deltas.
Well, not
You need at
necessarily.
least-
We could have proven it earlier with the other 2 data points. You just need 2 data points to prove at least one of the 3. Just because our first one failed doesn't mean the other ones are false. We just need more points to test the other ones. Because the first 2 points, we weren't looking at change.
Right, because there was no change. You just
But
said
it
that.
failed. But compared to the changes,
Right.
we needed another point.
Yeah.
So for each case, you
Each one of those
We're comparing the changes, so we did 2 changes.
Yeah.
Yeah, so we did 2.
Yeah, we wanted to know.
So it's 250. So the change in this is 250. Ready? Yeah. And what's the reason?
Okay, let's hear some. Now we have some more information. Let's hear Anna. What you guys talk about at your table?
They think that it's not proportional.
When you say it's not proportional, what's it?
They're not proportional. So painter 1 is not proportional to
What about painter? So painter 1 and painter 2, those aren't quantities. What quantities are you talking about?
the square feet painted by the
Okay. So so that we had kind of concluded that before. So you're saying that this kind of confirms it even more? Okay. What about so Kyle? What about the changes in the quantities? We can talk about that.
We solved it. So the first one was like the top one was 8 over 5, like relatively. The second time it was 13 over 9. This time it was 41 over 30. So it was like completely different numbers.
Okay, so you're still talking about the total amount painted, is that right? By each painter. So what about the changes in the amount painted? Did you guys talk about the changes in the amount painter at this stage? What's that? Negative 5 over 4. So talk to me about the process. So where's this coming from?
It's a yes 650 subtract 400 over with 450 subtract 250. Like the changing of y
Okay.
for the painting 2 over the changing of the painter 1.
So you were looking at taking the change of y over the change in x?
Yes.
And what was, tell me one calculation you did there.
650 subtract 400.
Okay. Negative or positive?
I get 650. Oh yeah, positive.
Okay.
Over 450 over and subtract 250 will be 200. So divide that, you will have 5 or 4.
So it sounds like you have corresponding values of the changes, right? And you said 250 or 200 here corresponded to 250. And you got 5, you said 5 over 4.
Yes. So that the x will be 4 and the 1 will be 5.
Okay. Let's see. Kyle, what did you guys talk about at your table?
We were talking about, we were taking the changes of both 400 and 650 and seeing how much of the change that was compared to going from 650 to 1025.
Okay, so you found that now the total amount by painter 2 you said was what?
Was 1025.
1025, okay, and?
And then that one's 750.
This one's 750, okay. And those are corresponding values? Best dotted line I've drawn all day. Okay, and?
And then computed the change from 450 to 750 compared to the change in 650 to 1025.
Tell me what those were.
I think it was the same thing. It was the same thing as 5 over 4. So.
Okay, well let's actually do it. So what was that change?
75 minus 1.
You said you took the change from 450 to 750. What is that change?
Oh, that's 200. Wait, that is 300.
Okay. And that is?
That is. Oh, I'm sorry. 375.
Keep going. So this is what you were talking about before now. So you compared those changes. So it's like you just kind of skipped. I just wanted to hear your whole process here.
Wait, so you want me to?
So what did you do with those changes?
We computed the percent change from 300 to 375 is the same thing as the change from 200 to 250.
Okay.
That's what we computed.
And how do you get? So is it what kind of change? Like, it went up 75?
No, it was a constant rate of change.
Okay. So we want to justify that. Somebody, Steven.
So we do the same thing as we did for the 250 and 200. So you take 375, which is your change in Y.
Okay.
Divide it by 300, which is your change in X, and you'll get 5 over 4.
Anything to add?
I want credit for coming up with all that.
What'd you say?
I just want credit for coming up with all that. Like, I just felt like I did all the work, and then it just like it just.
Yeah, but you weren't really justifying your reasoning too well. Sorry. Yeah, I was.
No, I understand that. It's just like I felt like I didn't feel good.
Okay. Sorry, Matt.
It's the growth factor that is proportional. It's not that it's a different, I guess, number that we're comparing.
Okay.
Because the first one we were looking at the total square feeted, not feeted, that's the time for the year. But we're looking at how much they had painted total wasn't proportional, so we had to ask for more numbers, more information now to compare to change.
Okay.
So it's a growth factor.
Okay. Anything else to add? All right. So what was our overall conclusion here? Total amount painted by painter 1 and painter 2?
The ways in which they
Okay.
paint a covariant is proportional.
Okay. So this number 5/4. You also say 1.25. I want you to come up with as many interpretations of that number as you can. What does that number mean, 1.25? So let's talk about it first. How many different interpretations can you come up with?
So it's 100% of what plus 1 to 2 will be
For every change in x, you get 1.2. For every change in x, you have 1.25 for that change of y. It's not the same thing. Growth factor is not the same as scale factor. It's not a growth factor. It's
one.
For every one change in x, your y change is 1.25. So change delta y equals 1.25 delta x.
Okay, so let's go through. We'll go through all the tables to see if we come up with 4 different things. So this table, you guys, what did you come up with?
Okay, that delta y equals 1.25 times delta x.
And can you talk about that? And so he's saying this. So can you talk about that in terms of the quantities, the painters?
So
what does this mean?
For every change in x, the y changes for 1.25 times that change in x. So for every 1 square footage change in x, y changes 1.25 square feet.
Okay, so how about somebody else? Can you talk about the painters in that same context? That's true. It's true.
The rate at which painter 1 paints is.
You're going with something new now. So we want to. So can you just talk about this relative to the painters?
Painter Y paints 25% more than painter X.
Okay. All right, cool. Next table. Yeah, that's true. That's true. I so it's true. Delta Y is 1.25 delta X. What does that mean for specifically mean for the painters? Exactly what does it mean for the painters? Yeah.
Painter Y paints 1.25 times as fast as, or painter 2 paints 1.25 times as fast as painter 1.
Okay, that's true, but that's a different conclusion. So that's slightly different than what this says, and it's true. So everything that we say at these tables are all going to be very closely related, but what you said isn't specifically what that says. You see, it's equivalent, but it's not the same. So what exactly does that statement say relative to the painters?
So for each additional square foot that painter 1 paints, painter 2 would be an additional 1.25.
It's actually still different. You're saying that painter 1 has to paint 1 square foot additional. Is that what that says?
No. Each change.
So what does that say? Anyone else want to give it a shot?
For every square foot or any amount that X paints, Y will paint that plus another 25% of what X did.
Okay. Right. So given some additional amount that painter 1 paints, painter 2 will paint 1.25 times as much as that. His additional amount will be 1.25 times as much as the additional amount that painter 1 painted. All those things you're saying are right, but they're not exactly this statement, you see. Okay, cool. How about this table? Something new. Not that we have like 4 or 5 things, but did you guys come up with a different way, the different meaning of the 1.25?
Well, we said each additional change of square foot painted by painter 2.
Well, I think for every square feet that painter 2 paints depends on how much painter 1 painted.
Go with painter 1. So for every square foot that painter 1 paints, make it easy on yourself.
Every square foot that painter 1 paints, painter 2 will paint 1.25.
1.25. for every 1 square foot, oh, sorry, there's an arrow in there that got, for every square foot that painter 1 paints, what does painter 2 do? Paints 1.25 square feet, right? Because you just said painter 1's painting 1 square foot, right? So painter 2 paints 1.25 square feet. So times as much, that's the first one. So whatever additional amount that painter 1 paints, painter 2 paints 1.25 times as much. That was the first one. This one, now you're saying that for every 1 square foot, painter 2 is going to paint 1.25 square feet. Okay, was there a different one you guys had at this table? Same? How about this table? So another one was mentioned. Do you guys have another one? So someone said painter 2 is painting 1.25 times as fast as painter 1. What do you think of that? True? So I heard that one. That one came out. So again, it's the same number. So they all feel the same, but they all are slightly different. Do you see? And then one more to throw out there. What is that number? That number 1.25 is the quotient or the ratio of delta y to delta x. So what does quotient represent? What does quotient represent? What's that? Constant ratio. But so when you divide 2 values, what does it represent? You get that answer.
Measure of one term in terms of the.
So which?
Measure of the numerator in terms of the denominator.
Yeah, so it's like your measure. It's a measure of how much additional painter 2 paints in the unit of how much painter 1 paints. So again, obviously very closely related, but a slightly different way of looking at it. So that's also called relative size. So it's the size of the additional amount painted by painter 2 relative to the amount painted by painter 1. So there's this relative size of additional amount painter 2 to painter 1. It's always 1.25. Okay, so is the total amount painted by painter 2 proportional to the total amount painted by painter 1? The changes, are they proportional?
Yes.
Do we have constant rate of change?
Yes.
Yes or no?
Yes.
Yes. Okay, cool. So how does constant rate of change show visually? Anybody? So in terms of visual representation, what are some possible visual representations of constant rate of change? Jackie?
You drew the dotted lines, which would be like the slope between the two, and since they're parallel, that means they're having the same slope.
Okay, so she's offering up that these slopes are parallel. What do you think about that?
Well, the last one looks kind of funky. Is it just bad drawing?
Well, they're parallel if they have the same slope.
Okay.
I mean, which they
We
do.
verified
So.
that the second and the third points do have the same by numbers 5 and 4.
What do we think about that? Everyone agree with that? Those lines should have the same slope. Richard, are you shaking your head?
I know, it doesn't look that way.
Can we do do some extreme examples to test your hypothesis? So can you come up with some extreme examples to test this idea of will those be parallel if you have constant rate of change? So see if you can come up with a way to convince yourself either one way or the other. Okay, one way or the other.
still be hard for us. So that means that one would go to like it's a
Why is the amount of page
that one would go to
so it's going to slowly get farther and farther ahead of that. So the sense of that line, eventually, they're going to get really far apart. They're both still going the same direction, but this one's much faster.
That's the wrong graph.
Yeah.
That's one thing to change that exponential.
They both start in the same
It's their changes that are proportional, not their total.
I don't know what you're saying is exponential, but what's exponential? Like, what is it? No, seriously, I don't understand what you're saying is exponential. Those lines that we're talking about?
What do we think?
No, the speed is proportional. The amounts. Speed is the rate of change. Right, which is the speed.
Did anyone take my advice and come up with something? So, I don't feel like you guys took my advice. Anyone take my advice? What'd you do?
Discussed going to infinity.
Okay.
So top line would go to infinity 25% faster. So in a huge extreme example, the top line would be like much longer than the other.
Okay.
So your slope is going to get flatter as you get.
What about a really small example?
It's going to be almost straight up and down.
So here's a 25 and 1.25 times 25. Is that going to be parallel to these? No. Okay. So what is maintained? So the let's see. Anyway. Okay. So I don't want to go there. So for time's sake, let's move on. But so another way we can depict this is so you're thinking about slope, and so why doesn't slope work the way I have it set up? So what's the problem?
Because the changes in the
well, I don't know if I'm right, but we found out that they're not proportional, which means that at some point there's like a plus B, because one person started out with more pain.
Okay.
But on this little bar graph right here, they start in the same place, so it's not an accurate representation of their relationship.
Okay, so I'm tricking you. So it's not. Okay. What do you think about this? Does what I've shown you imply? What you're saying is it implies that when x was 0, y is 0. What I've shown you. Does it?
Because you don't know what your x is.
Well,
So by the graph you're saying yes, I'm showing 0, 0 here.
but the problem says they both start. So if they start at the same time,
Did they say that? They said they have
started.
oh,
What's the change of 250 result in?
And if they started at 0, 0,
oh, that's right. We wouldn't
If they
know.
if they started at 0, 0 and they're change proportional, they would have to have been, their amounts would have been proportional. Because if they changed the same, if they had started at 0, they couldn't, their amounts would have to be proportional. If they change the same amount, they both start at the same time, they have to be proportional.
Okay, so for time's sake, I'm just going to fast forward here. So I think the reason that the confusion came with the slope, thinking that the slope should be equal, is because how are we used to seeing two quantities represented visually together? Yeah, as a line, but in what system, right? In what system? Why is the system different?
Both quantities are traveling in the same direction. Well,
Okay, so I'm showing y here as horizontal, right? And you're used to
the slider will turn it vertical.
okay, so this is what you're used to, right? This is what you're used to, showing the y amount in the vertical axis and the x amount horizontally. I'll come back. Okay, so let's do that. So we're going to look at what you're more used to. And so what happens every time painter 1 paints a certain amount, painter 2 paints how much?
1.25 times that amount.
1.25 times that amount. Okay, and so we could turn, so really we're tracking, the two quantities tracking together is really tracking that point right there, right? So let's do that. It's not letting go. Okay, there we go. So we're going to track that top of that blue bar as the two quantities change together. And the black is leaving a trail of points. Okay, so as painter 1 paints 100, ignore the axis numbers. So the blue lines are still 100. So the grid lines are 100 square feet each. Okay, just ignore the axes values. As painter 1 paints 100, how much does painter 2 paint? Right, 1.25 times as much as that. So if delta x is 100, delta y is? And if painter 2, from there, if painter 2 paints 300, say 1, 2, 3. How much will painter 2 paint?
375.
Right, 1.25 times 300. Okay, so this is the basis of a linear function, that you maintain the relative size of changes in y to changes in x. And what is that relative size that we have? Yeah, and that's, okay. For every amount that we go, doesn't matter what it is, so this is just some arbitrary amount now. How much does painter 2 amount painted paints?
1.25 times the change.
Right. Okay, so we can use this to form what's the equation of the line, which will give us all corresponding values of painter 1 and painter 2. Okay, so here's what we're going to do. So what was the starting amount? So, okay, so first, so we can represent every point on that line. I'll make a black point. So I can pick any point to represent every point. How can I do that? So I'm going to pick this point right here, say. How can I make that represent every point on the line?
You find the delta.
I can call it x, y, right? So now, so it doesn't matter where I chose it. I'm just saying that can be every point on the line. Okay, so let's look at so we've got the starting value of painter 1 and painter 2, and a final value of painter 1 and painter 2, which is just, it's allowed to change, right? It can be any corresponding pair along here. So we'll start by asking, what's the change in x? So, let's see. Daniel, what's the change in x?
Is it x minus 250?
He's asking, is it x minus 250? Jessica, what do you think? Agree? Victoria, what do you think? Yeah. But we like having a change in x. Why? Because what can it tell us? Yeah, we always know with constant rate of change, we know the corresponding change in y. So, Janae, what is the corresponding change in y?
To me, it would be y minus 400.
Y minus 400. Okay, that would be one way to express it. Can we express it in terms, that's true, y minus 400. Can we express it in terms of delta x? So how can we express it in terms of delta x, Kathy?
Isn't it 1.25 times x minus 400?
Yeah. $250? But look at that. So can I just add 400 to both sides? And what do we have? So we found that equation on that line using the idea of constant rate of change, that the amount painted by painter 2, the additional amount painted by painter 2, delta y, is always 1.25 times the additional amount painted by painter 1. So it was all right. That was it right there. So that change in y minus 400 is the same as 1.25 times the change in x. Okay, so we call this point, as things move. Let's see if I can bring it back here. So we call this point slope form. This is important for an assignment you have for next week, okay? For Monday. All right, so point slope form means if you have a point and you have the constant rate of change, you can write the equation of the line. Now I want you, in the last 2 minutes, you got 2 minutes? I want you to use the same process. So start over and find how much had painter 2 already painted when painter 1 started. Use the same process to figure out how much had painter 2 painted when painter 1 started, and then painted none. Exactly. So use the same process. Start over. Start over. Yeah, so start over. You can choose this point or another point, but we got this point up there. So if you're not sure, work together with somebody else. Everyone's going to do it. Yeah, start over. Use this process, same process. Start over. Use this process right here to determine that how much will painter 2 have already painted when painter 1 started, and it was at 0.
So painter
So yeah,
started,
so it'd be
x would be 0, right?
So well, we would reverse it. It would be 2. If I'm starting from that point, we would
I'm just thinking, what would our x value be? When painter 1 started,
x would be 0. So it would be 5. So delta x would just be 250.
0 minus 250.
Yeah, and delta y would be 400 minus.
It's 400
because we don't know y.
Right.
We just know that x will be 0.
Right. Well, it'd be y minus 400. Yeah. And we know that.
Well, it'd be 400 minus y.
Yeah.
Because y is to the left, so now we want to
400 minus
here.
that quantity.
No, it's still y minus
300
Oh yeah.
12. Which gives you 87.
So we know that delta y equals y minus 400. We know that delta y equals 1.25 times delta x, which we found is negative 250 in this case. So we have 1.25 times negative 250 equals y minus 400. So we can add 400 over. So we get to the same point you did, but starting over.
Okay. So 67.5. So it'd be minus 300. 312.5. So yeah, 312.5. So we're off with 87.5.
Okay, so quickly, I don't want to keep you over too long.
I just did 400 minus 2.5.
Sorry, you skipped us so mentally.
You can't read my mind?
No, I can't.
Okay, so Steven, did you get the change in x for this situation?
Yeah, I put 250 minus x.
250 minus x. Okay, so what are we really after here? We're trying to get the amount painter 2 is painted when painter 1 is painted how much? 0, right? So from 250 are we decreasing the amount that painter 1 painted or increasing?
Decreasing.
So the question is by how much?
250.
So delta x should be? Daniel. 250 minus 0 or 250? Agree with that? What do you think over here, Rochelle? What is delta x?
What is delta x?
Yeah.
Negative 250.
Negative 250.
We're going down.
Yeah, because we're decreasing the amount, right? So if we're here and we want to know something corresponding to x equals 0, we just decrease. So it would be 0 minus 250, right? Okay, corresponding change in y. How would we calculate the corresponding change in y?
1 minus 400 equals like 1.25 times with negative 250. Oh, I just setting it up. The delta y will be 1 minus 400.
Y minus 400? Equals?
To 1.25 times with negative 250.
So changes in y are always 1.25 times the change in x.
Y will equal to 87.5.
Did it work? Okay, so I will do my best to post Monday's stuff as soon as I can. Today, hopefully. And yeah.
Are you did you record this live?
Yeah, it's all video.
Okay, how do we access it?
So the videos are at, there's an area on Blackboard called Class Videos, and then it's a YouTube link.
Okay.
So that will be up later tonight.
So yesterday I did